Okay, thank you. Okay, Bismillah Rahman Rahim. This is lecture number 3 of the course Irrigation Engineering. In today's lecture, we will discuss about the crop water requirements and its measurement. Water requirements of crops. The term water requirements of crops means the total quantity and the way in which a crop requires water from the time it is sown to the time it is harvested. So what we mean by the water requirements of crops, it means the total quantity and the way in which a crop requires water from the time it is sown to the time it is harvested. This is known as water requirements of crops. Different crops will have different requirements, and the same crop may have different water requirements at different places of the same country, depending upon the variations in climate, type of soil, methods of cultivation, and useful rains, etc. So different crops, they require different amount of water for their growth, and the same crop may have different water requirements at different places of the same country, depending upon the variations in climate, type of soil, methods of cultivation, and useful rains that fall over the crops during the growth period. So different crops will require different amount of water, but the same crop may require different amount of water at different locations of the same country, depending upon the climate, the type of soil, methods of cultivation. Irrigation requirements of certain crops. So in this table you can see that we have the kharif crops, the summer crops. So for example, we have maize. Its period of growth is June to September, October. The average water depth that is required, that is 45 centimeter. This is the average water depth that is required to grow the maize. Now irrigation requirements, 4 or 5 waterings, sensitive to drought. If we have less quantity of water is available, then this crop is very sensitive to that. And on the other side, if floods occur, again it will cause damage to maize. Responsible to fertilizers, average quantity of seed required kg per hectare, that is 15, and average quantity of yield obtained, that is kg per hectare, 3000. So this is a general information regarding the maize. For example, we can consider cotton. So it is period of growth is May, June to November, January. The average water depth required, that is 25 to 40 centimeter. 3 or 4 irrigations are required. Damage up to the extent of 50% may be caused by flooding, rains, etc. and average quantity of yield obtained, that is 500 kg per hectare. Similarly, you can see that we have this till here. This is an ancient crop that is used to obtain the oil. This is the period of growth and generally does not require much water. You can see here, not mentioned. Generally not irrigated, but better to irrigate once. And the average quantity of seed required, kilogram per hectare 1.25, and average quantity of yield obtained 350 kg per hectare. Next, we consider some rabi crops. These are winter crops. So we have wheat ordinary, that is the period of growth, that is October to March, April. Average water depth required, that is 37.5 centimeter. 3 to 4 watering of 1 to 2 meter depth. The seeding, average quantity of seed required, that is 80 to 100 kilogram per hectare, and the average quantity of yield obtained, that is 1500 kg per hectare. For example, we consider potatoes. So the period of growth, that is September, October to February. The average water depth required, so 60 to 90 centimeter. Usually irrigated, sown in high hills up to early April. Second crop in plains is sometimes taken in February, April. The seed that is required, kilogram per hectare 15,000, and the crop yield, that is 35,000 kg per hectare. Similarly, you can see that we have sugarcane here. So February, March to December, March, you can see that sugarcane is almost grown for the entire year, and the water depth that is required, average 90 centimeter. 5 to 6 waterings of 10 centimeter or more required. The seeding, that is 500 kg per hectare, and the crop yield 25,000 to 30,000 kilogram per hectare. So this is some general information. The irrigation requirements of certain crops to get some idea. Next, we discuss the crop period or base period. Some basic concepts. The time period that elapses from the instant of its sowing to the instant of its harvesting is called the crop period. So what is the crop period? It is the time period that elapses from the instant of growing a crop to the instant of its harvesting. That time period is known as the crop period. The time between the first watering of a crop at the time of its sowing to its last watering before harvesting, it is called the base period. So base period, it is the time that elapses between the first watering of a crop at the time of its sowing to its last watering before harvesting. This is known as base period. So you can see that there is a slight difference between the crop period It is the time period that elapses from the instant of sowing a crop to the instant of harvesting. That is crop period. Whereas the time between the first watering of a crop at the time of its sowing to the last watering before harvesting is called the base period. So it means that the crop period is slightly more than the base period, but for all practical purposes, they are taken as one and the same thing and generally expressed in B days. So B days, we will denote the crop period and the base period is practically considered as the same, and it is denoted by B days. Next, we discuss delta of a crop. Each crop requires a certain amount of water after a certain fixed interval of time throughout its period of growth. So each crop requires certain amount of water after a certain fixed interval of time throughout its period of growth. Just like we saw in this table here, you can see that maize, the average water depth required, that is 45 centimeter. And then it has to be provided the irrigation requirements, the artificial supply of water for the growth of maize. So 4 to 5 waterings. So each crop requires a certain amount of water after a certain fixed interval of time throughout its period of growth. The depth of water required every time generally varies from 5 to 10 centimeter depending upon the type of crop, climate and soil. So we have different crops, they require different amount of water. So that is why the depth of water required every time generally varies from 5 to 10 centimeter depending upon the type of crop, the climate of that area and the soil conditions. The time interval between two consecutive watering is called the frequency of irrigation, and it is also known as the rotation period. So the interval, the time interval between two consecutive waterings, this is known as frequency of irrigation. It is also known as rotation period. This total depth of water in centimeter required by a crop to come to maturity is called its delta. This is known as delta of a crop. So it is the total depth of water in centimeter required by a crop to come to maturity is called its delta. It means that one crop, it requires, let's say we have this wheat here, it requires 37.5 centimeter of water on average. So this is the delta for the wheat. This is what we mean by delta. The total depth of water in centimeter required by a crop to come to maturity is called its delta. For example, if rice requires about 10 centimeter depth of water at an average interval of about 10 days and the crop period for rice is 120 days, find out the delta for rice. Water is required at an interval of 10 days for a period of 120 days. Therefore, number of required waterings, that will be 120 by 10, 12 waterings will be required. Therefore, total depth of water required, that will be equal to number of waterings multiplied by depth of each watering. So that is 12 multiplied by 10, 120 centimeter. Hence, delta for rice, that is 120 centimeter. This is the total depth of water that is required by the rice to come to maturity. Average approximate values of delta for certain important crops. For sugarcane, delta on field is 120 centimeter or 48 inches. For rice, it is again 120 centimeter or 48 inches. Garden fruits, 60 centimeter. This is the delta on field. For cotton, 50 centimeter or 22 inches. For vegetables, delta on field, that is 45 centimeter or 18 inches. For wheat, it is 40 centimeter or 16 inches. Maize, 25 centimeter or 10 inches, and other crops. So this is the delta, the total depth of water required for these crops to come to maturity. During the growth period, this is the total depth of water required for their full growth. Next, we discuss some important units. So we discuss the acre foot. You can see here that we have this 66 by 660. So this is the area. 1 acre has this much square feet. 1 acre, that is equal to 43,560 square feet. So 66 multiplied by 660 feet. So this is equal to 43,560 square feet. So 1 acre is equal to this much square feet area. Now, if we have a water over this area to a depth of 1 foot, so this become acre foot. This is the unit of volume. So you can see that 1 acre foot, that is equal to 43,560 cubic feet. This is the unit of volume. So in the previous lecture, we discussed this unit in detail when we discussed the water budget of Pakistan. So million acre feet, million is 10 power 6. And acre feet, that is the volume unit. So 1 acre foot, that is equal to 43,560 cubic feet. So we have 1 acre, and if we have the depth of water over this 1 acre, so this is known as the volume, that will be 1 acre foot. Similarly, we have 1 hectare, that is equal to 10 power 4 square meter. 1 hectare, this is equal to 10 power 4 square meter. And then 1 acre, so that is equal to 0.4047 hectare. This is how we can convert from hectare to acre and acre to hectare. Next, we discuss a duty of water. So the duty of water is the relationship between the volume of water and the area of crop it matures. Duty of water is the relationship between the volume of water and the area of crop it matures. How we can define it? It may be defined as the number of hectares of land irrigated for full growth of a given crop by supply of 1 cubic meter per second of water continuously during the entire base period of that crop. So how we can define the duty of water? The number of hectares of land irrigated for full growth of a given crop by supply of unit cubic 1 cubic meter per second of water continuously during the entire base period of that crop. Clear? So this is the duty of water. We can also define in the FPS system that the number of acres of land irrigated for full growth of a given crop by supply of 1 cubic feet per second, 1 cubic of water continuously during the entire base period of that crop. So it means that for water that is flowing, unit discharge of water that is flowing for B days, that is the base period of that crop, that matures D hectares of land. So that will be the duty of water. D hectares, the number of hectares of land irrigated for full growth of a given crop by supply of unit discharge continuously for the entire base period. So that is known as duty of water. If water flowing at a rate of unit cubic meter per second runs continuously for B days and matures 200 hectares, then duty of water for that crop will be defined as 200 hectares per cubic. The duty of water that will be represented by D. So unit discharge flowing over an area for irrigation of a crop for the base period, the number of hectares of land irrigated, so that is known as the duty of water. A relationship between duty delta and base period. Let base period of the crop be B days and 1 cubic of water be applied to this crop on the field for B days. Now volume of water applied to this crop during B days, that will be equal to B multiplied by, because B is in days, so multiply by 24 hours, multiply by 60 minutes and then 60 seconds. Clear? So the idea here is that we have, for example, 1 cubic meter of water. This is the volume. So this is for 1 second. This is for 1 second. Clear? 1 cubic of water. Now the volume for B days, we want to find out that what will be the volume if it is flowing for B days. So that will be equal to 24 multiplied by 60 multiplied by 60. Clear? So this is in cubic meter. This is how it comes. So this is equal to 86,400 B cubic meter. Now, by definition of duty, 1 cubic meter supplied for B days matures D hectares of land. So this quantity of water matures D hectares of land, or 10 power 4 into D square meter of area. So the total depth of water applied on this land, that will be simply equal to volume by area. So we have this volume and this much is the area. So by definition, this total depth of water is called the delta. So delta, this is equal to 8.64 B by D. This delta will be calculated in meter or multiplied by 100. So delta is equal to 864 B by D in terms of centimeter. So delta is in centimeter, B is in days, and D is the duty in hectares per cubic. So this is the relationship between the duty of water, delta of crop, and the base period of the crop. Like this, in the FPS system, we will get this relationship for the delta. Delta is equal to 1.985 B by D, or it can be approximately taken as 2 into B by D. So delta will be in feet. So delta will be in feet from this equation. B is in days and D is the duty in acres per cubic foot per second. Next, we discuss factors affecting the duty of water. The type of soil. So we have coarse grained soil, percolation losses will be high, and this will result into low duty. When water is lost, then the area that it will irrigate, that will decrease. So it will result into low duty. Clear? Because you see here the duty definition that we defined here is that the number of hectares of land irrigated for full growth of a given crop by supply unit discharge continuously during the base period. So if there are losses, then what will happen? The number of hectares of land, that will decrease. So it will decrease the duty of water. So we have coarse grained soil, percolation losses are high, and this will result into low duty. Fine grained soil, percolation losses are less, and this will result into high duty of water. Next, we have type of crop. So let's say we have crop A that requires large quantity of water. This will result into low duty of water. And if we have crop B that requires less quantity of water, this will result into high duty of water, because water will irrigate more land area. Structure of soil. So good structure of soil is called good tilth of soil. Tilth of soil, the physical condition of the soil. So we have good structure of the soil. Evaporation losses are less, and this will result into high duty. Again, we have good structure that is properly aerated because of large voids. This will result into a yield of crop increased. So you can see here we have compacted soil and we have good soil tilth. So the physical condition of the soil is good. You can see here the good structure, evaporation losses are less, it will result into high duty, and the soil that is properly aerated because of large voids, that can result into yield of crop that is increases. Next we have slope of ground. So we have steep slope, downstream portion get more water, upstream portion remain drier, so this will result into low duty of water. Properly prepared field will result into equal distribution of water, and this will result into high duty of water. Water will be able to irrigate more land area, so this will result into a high duty. Next we have climatic conditions. So temperature and wind velocity are high. This will result into more evaporation losses, and as more water is evaporated, so this will result into low duty. If we have rainfall during base period, then less irrigation requirement, and therefore it would mean high duty of water. So it means that during rainfall, the crops already get some water, so less quantity of water will be required to bring it to the maturity. So it means that less irrigation requirement, this means high duty. Method of cultivation. So not properly plowed and method of cultivation is faulty and less efficient, so this will result into low duty of water. If land is not properly prepared for cultivation, so in that case the proper irrigation cannot be done, and this will result into low duty. Properly plowed and made quite loose, water retention capacity increase, number of watering that will reduce, and this would result into high duty of water. So that's why you can see that land preparation during the sowing of the crop and then supplying the water to the crop, this is very important. System of irrigation. Non-perennial. Perennial means that the water is continuously flowing. So non-perennial means that water is not continuously flowing. Only during flood season the water is available. Wasteful use of water. that can result into low duty. When we have perennial system where water is available in adequate quantity throughout the base period, so water application throughout the growth period, soil remains continuously wet and less quantity of water will be then required. So this will result into high duty of water. So during the flood season, we supply more water, you can see here, than is actually required. This results into wasteful use of water and consequently the duty of water that is low. But when in perennial system, we have already the water that we can supply. So soil remains continuously wet. This will result into less quantity of water and the result would be a high duty of water. Application of water. We have drip irrigation system that is the most efficient. This will result into very high duty of water. As we studied in the previous lecture that in drip irrigation system, through a network of pipes, we supply the water directly underneath the plants and crops. So this results into saving of water. This is most efficient and consequently for this application of water, the water has very high duty. For sprinkler irrigation system where we sprinkle the water over the crops, the seepage losses are reduced as compared to the flooding techniques. So this sprinkler irrigation is in the form of artificial rain and it results into high duty. It is less than the drip irrigation system, but still it results into high duty. Now the surface irrigation system, the flooding techniques where we flood the area of the crops with water, so this results into more waste of water and consequently then the duty of water that is low. So these are some of the factors which affect the duty of water. Next we discuss consumptive use or evapotranspiration. Consumptive use may be defined as the total amount of water used by the plant in transpiration, that is building of plant tissues, etc., and evaporation from adjacent soil or from plant leaves in any specified time. So this is consumptive use. This is also known as evapotranspiration. And consumptive use is the total amount of water used by the plant in transpiration, that is building of plant tissues, etc., the water that the plant use for its growth, and evaporation from adjacent soil or from plant leaves in any specified time. So what is the difference between the delta and the consumptive use? You see that the delta of the crop that we studied, that is for the whole period. That is for the whole period of the crop growth. So the total depth of water required during the entire growth period of the crop, that is known as a delta. This is we define delta. Whereas the consumptive use, that is the total amount of water used by plant in transpiration and evaporation from adjacent soil or plant leaves in any specified time. This is not for the entire crop period. This is in any specific time. So this is known as consumptive use or evapotranspiration. The values of consumptive use may be different for different crops and may be different for the same crop at different times and places. So because the crops, they require different amount of water, so consequently you can see here that the values of consumptive use, it is different for different crops, and again it may be different for the same crop at different times and places depending upon the climate conditions, the soil conditions. So factors affecting consumptive use, the different factors that affect the consumptive use are the same factors on which the transpiration and the evaporation depends. For example, we have temperature. So if temperature is more will be evaporation and transpiration. Consequently, consumptive use will be more. So sunlight, for example, plants, they require building of the tissues, photosynthesis process. So if we have sunlight that is available, plants transpiration, that will be more. Similarly, humidity, wind movement. So if we have more wind blowing, you can see that evaporation from the surface, that will increase because the wind will take away vapors and therefore the rate of evaporation, it will increase. Similarly, we have the soil topography, the precipitation, method of irrigation, depth of water applied for irrigation. So all the factors on which the transpiration and evaporation depends, consumptive use or evapotranspiration will also depend on all those factors. Next, we defined effective rainfall. So precipitation falling during the growth period of a crop that is available to meet the evapotranspiration needs of the crop is called effective rainfall. So in agriculture, in irrigation, we define the effective rainfall is that precipitation falling during the growth period of crop that is available to meet the evapotranspiration, this consumptive use, or evapotranspiration to meet the evapotranspiration needs of the crop is called effective rainfall. So it does not include precipitation loss through deep percolation below the root zone or the water lost as surface runoff. So we have precipitation, that part of the precipitation that is used by the crops in meeting the evapotranspiration needs, that is known as effective rainfall. This effective rainfall, it does not include precipitation loss through deep percolation, that is the water infiltrates into the soil and then travels downward, that is known as percolation. A deep percolation, that this water through the percolation joins the groundwater zone of saturation, so deep percolation below the root zone, because this water, if it travels vertically downward below the root zone, then the plants will not be able to extract this water. So that's why it will not be part of the evapotranspiration needs, the water that the plant extract. And the water lost is surface runoff. You can see that in hydrology, you might have studied that we have total rainfall. We have the total rainfall and minus abstractions. Abstractions are all the losses. Abstractions. Abstractions. So total rainfall minus the losses, that for example can be the water infiltrated, evaporation, and other depression storages. So this was actually the water that appears as surface runoff. So this was actually called as effective rainfall in hydrology. Clear? This was called as effective rainfall that appears as surface runoff. Effective rainfall. But you see that then there was a confusion, because in irrigation or the people in agriculture, so they say that this effective rainfall is that part of the rainfall falling during the growth period of crop that is available to meet the evapotranspiration needs of the crop, that is known as effective rainfall. So consequently, then in hydrology what we did is that we actually then call it as excess rainfall. We now call this as excess rainfall. That is the rainfall that appears as surface runoff. And we reserve this effective rainfall as precipitation falling during the growth period of crop that is available to meet the evapotranspiration needs. Next, we define consumptive irrigation requirement. It is the amount of irrigation water required in order to meet the evapotranspiration needs of the crop during its full growth. It is the amount of irrigation water required in order to meet the evapotranspiration needs of the crop during its full growth. It is therefore consumptive use exclusive of effective rainfall, precipitation, stored soil moisture, or the groundwater. So irrigation water that artificially we have to supply. Clear? So it is that amount of irrigation water required in order to meet the evapotranspiration needs of the crop during the full growth. That water that we have to artificially supply, that amount of water. So that is known as consumptive irrigation requirement. It is therefore consumptive use exclusive of effective precipitation, stored soil moisture, or groundwater. So consumptive irrigation requirement. So this is equal to consumptive use minus effective rainfall. Next we have net irrigation requirement. It is the amount of irrigation water required in order to meet the evapotranspiration needs of the crop as well as other needs such as leaching of salts. Net irrigation requirement. So in addition to meet the evapotranspiration needs of the crops, we will need to supply the water for leaching of salts, removal of salts from the soil. Because in the soil, sometimes the salts are present. These are not beneficial. That is because of which we have salinity, harmful salts. So how to remove them? We have to provide some additional water that can dissolve these salts, and then that water can be drained either surface drainage or subsurface drainage to remove these salts. This is known as leaching of salts. So net irrigation requirement, it is the amount of irrigation water required in order to meet the evapotranspiration needs of the crop as well as other needs such as leaching of salts. So net irrigation requirement, it is consumptive use minus effective rainfall plus water lost in deep percolation for leaching. Another term, that is field irrigation requirement. It is the amount of water required to meet net irrigation requirements. Now net irrigation requirement, this is net irrigation requirement. Amount of irrigation water plus other needs plus water lost in deep percolation for leaching of salts. So it is the amount of water required to meet net irrigation requirements plus the water lost in percolation in the field water courses, field channels, and in the field application of water. It is given by field irrigation requirement is then equal to net irrigation requirement divided by eta A, where eta A is the water application efficiency. Next we have gross irrigation requirement. It is the amount of water required to satisfy the field irrigation requirement. This is now the field irrigation requirement, and the water lost is conveyance losses in distributions up to the field. So in the above you can see that is the water lost in percolation, that is the seepage losses that can occur here, and in here is the water lost is conveyance losses when we convey the water in distributions up to the field. So in this case the gross irrigation requirement, that is equal to the field irrigation requirement divided by eta C, where eta C is the water conveyance efficiency. So this is how we can calculate the gross irrigation requirement. Next we discuss the potential evapotranspiration and actual evapotranspiration. What is the difference between the two terms? So we know that evapotranspiration is the total loss of water from farmland as evaporation and from plants grown on it as transpiration. If sufficient moisture is always available to completely meet the needs of the plants the resulting evaporation is called potential evapotranspiration. So it means that evapotranspiration, that is evaporation plus transpiration from the plant leaves under unlimited supply of water. When there are no limitations on the supply of water, you see, if sufficient moisture is always available to completely meet the needs of the plants, under that condition, the evapotranspiration that will take place, that is known as potential evapotranspiration. The real evapotranspiration occurring in a specific situation is called the actual evapotranspiration. Whereas actually in the crops, we cannot have unlimited soil moisture or supply of water. So that is why the real evaporation or the real evapotranspiration occurring in a specific situation is called the actual evapotranspiration. Now, what is the concept of these two? So you can see here that this ETO, this is also known as the reference evapotranspiration or the potential evapotranspiration, but it's commonly called the reference because it is for a reference crop such as a grass. So we have this as the reference. You will see this terminology when you discuss evapotranspiration. So you will see that this is known as a reference evapotranspiration. A reference ET, evapotranspiration. Now this reference evapotranspiration actually we calculate by the use of equations are available, and this reference evapotranspiration we calculate. This is for a well-watered grass as a reference crop, so that's why this is known as reference evapotranspiration, and this is denoted by ETO in the literature. So because in this case this reference evapotranspiration, it is mainly a climatic parameter. You will see that when we calculate this, mostly we consider the climate data for that area to calculate this reference evapotranspiration. So in order to make it applicable to crops, clear? So that's why this ETO, the reference evapotranspiration, that is multiplied by a crop factor, that is Kc, and the crop factors that are calculated for the different crops, and these are available in the form of tables in the literature. So we multiply this reference evapotranspiration with the crop factor to get the crop evapotranspiration, so that it is reflected for that specific crop, well-watered crop, optimal agronomic conditions. Now it can happen that sometimes we have water and environmental stress due to the conditions of the soil. We can have water and environmental stress. In that case, we have to multiply this with another factor, that is for the soil, that represents the soil conditions in addition to the crop factor here. So this is how the evapotranspiration for the crop that is adjusted. But most of the time we are using this one here. We calculate this reference evapotranspiration, which will mainly depend on the climate conditions. You can see here radiation, temperature, wind speed and humidity in the equations, and then we multiply this with the crop factor that is calculated for the different crops to get the crop evapotranspiration. So these are some basic terms. Next, we study how to estimation of this consumptive use. Consumptive use or evapotranspiration for these crops. Clear? That we studied here. Consumptive use or evapotranspiration. So how we can measure this? We have direct measurement of consumptive use. For this, we have different methods available to us: tank and lessimeter method, field plot, experimental plots, soil moisture studies, integration method, inflow and outflow studies for large areas. Direct measurement of consumptive use. We can also calculate this consumptive use by use of equations that were developed. So those equations include the Blaney-Kreidel equation, Hargreaves plus A Penn evaporation, and we have the Penman's equation. So we discuss these methods in detail briefly. First, we have direct measurement of consumptive use by tank and lessimeters. So how we measure it? Tanks are containers set flush with the ground level, having area of 10 meters square. This is the area, and 3 meter deep. The depth is 3 meter. Larger the size of the tank, greater is the resemblance to root development. This will reflect more natural conditions. Consumptive use is determined by measuring the quantity of water required to maintain constant moisture conditions within the tank for satisfactory proper growth. So in this case, what we do is that the consumptive use, that is the water required by the plants to meet its evapotranspiration needs, by measuring the quantity of water required to maintain constant moisture conditions within the tank for satisfactory proper growth. This is how we are assessing the consumptive use. In lessimeters, the bottom is pervious. Consumptive use is the difference of water applied and that draining through pervious bottom and collected in a pan. So in lessimeters, the bottom is pervious, so the water is supplied to the crops that are grown in lessimeters, which are containers like water tanks. This one here, the tanks that is used to grow the crops. So in lessimeter, the bottom is pervious, so water is supplied to the crop that is grown in lessimeter. The crop will use the water for its evapotranspiration needs, and remaining water that will be draining through the pervious bottom, and that is collected in a pan. So the consumptive use is the difference of water applied and that water which is drained from the lessimeter at the bottom. So the difference of the two, the water applied and the water collected at the bottom, that is how consumptive use is calculated. You can see here that in tank and lessimeters, this is how the crops are grown and the water is supplied here. In case of the tank, so that is consumptive use is determined by measuring the quantity of water required to maintain constant moisture conditions within the tank for satisfactory growth of that crop. This is how we can estimate the consumptive use. And in case of lessimeters, then the water will be collected from the bottom, it will be pervious, and the water applied, and the water that is drained, the difference will give us the consumptive use. So these lessimeters, these are very expensive to install. Here we are trying to replicate the natural conditions of the growth of the crops by supplying the water. So this is actually very expensive to install. Plus these lessimeters, these are very sensitive instruments. So the water that is applied and then the water that drains has to be collected in a pan so that we can effectively measure the difference of water applied and the water drained at the bottom in order to calculate the consumptive use. The second method, that is field experimental plots. So in this method, irrigation water is applied to the selected field experimental plots in such a way, you see the area that will be divided into different experimental plots in such a way that there is neither runoff nor deep percolation. Yield obtained from different fields are plotted against the total water used, and as basis for arriving at the consumptive use, those yields are selected which appear to be most profitable. So the area is divided into different experimental plots. Irrigation water is supplied in such a way that there is neither runoff nor deep percolation. Yield obtained from different fields are plotted against the total water used, and as basis for consumptive use, those yields are selected which appear to be most profitable. It is seen from observations that for every type of crop, the yield increases rapidly with an increase of water used to a certain point and then decrease with further increase in water. At the break in the curve, the amount of water used is considered as the consumptive use. What we mean here, you see that if I can draw the graph here, so we have the water depth, that is the water that we apply to the crops. So we have the water depth. And we have the yield, crop yield. So what happens is that when we supply the water, the crop yield also increase, and when we continue to supply the water, then after certain condition, the crop yield will decrease. So you can see here, for that water where we have maximum yield, here you can see that we have maximum yield. At this point here, so this depth of water that is required, that will be the optimum depth of water. optimum depth. So this is what it says. It is seen from observations that for every type of crop, the yield increases rapidly with an increase of water use to certain point. You can see here up to this point here, and then decrease with further increase in water. So at the break in the curve, you see after this, the curve moves in the downward direction. The amount of water used is considered as the consumptive use. So we take a break here, and if there is any question, you can ask a question. Okay, so Bismillah ar-Rahman ar-Rahim. We were discussing the direct measurement of consumptive use. So we already discussed the field experimental plots. The third method is soil moisture studies. This method is especially suitable to those areas where soil is fairly uniform and groundwater is deep enough so that it does not affect the fluctuations in soil moisture within the root zone of the soil. So this method, the soil moisture studies, is suitable for those areas where soil is fairly uniform and groundwater is deep enough so that it does not affect the fluctuations in soil moisture within the root zone of the soil. Soil moisture measurements are done before and after each irrigation. The quantity of water extracted per day from soil is computed for each period. A curve is drawn by plotting the rate of use against time, and from this curve, seasonal use can be determined. So in this method, a curve is drawn by plotting the rate of use against the time, the quantity of water, the rate of use against time, and from this curve, seasonal use can be determined. So here you can see that in soil moisture studies, we need to measure the soil moisture before and after irrigation. The fourth one is the integration method. In this method, it is necessary to know the division of the total area under irrigation crops, natural vegetation, water surface area, and barren open land area. So the integration method is summation of the products of unit consumptive use for each crop times its area, means for the crops. Then we have unit consumptive use of native vegetation, any other vegetation that may be present, times its area, water surface evaporation times the water surface area, and evaporation from the bare land time its area. So you can see that in this method, the whole land area, the total area, that is divided into these different sections representing the crops, any natural vegetation, the water surface area, and the barren land. Thus, in this method, annual consumptive use for the whole of the area is found in acre feet or hectare meter units. So in this method, annual consumptive use for the whole of the area that is determined. The fifth method is inflow-outflow studies for large areas. So in this method also annual consumptive use is found for large areas. If U is the valley consumptive use, it is given by this equation. Now in this equation, all the terms, all the measurements, they will have the units of acre feet or hectare meter, because we simply add or subtract the different terms. So they must have the same units in order to add or subtract these quantities. So in this equation, U is the valley consumptive use in acre feet or hectare meter. I is the total inflow during the 12 months year. P is the yearly precipitation on valley floor. GS, that is the ground storage at the start, beginning of the year. GE is the ground storage at the end of the year, and R is the yearly outflow. So this is like a water budget equation to calculate the annual consumptive use, and this is used for large areas. Next, we discuss consumptive use determination by use of equations. We have different equations are available to us that we can use to calculate the consumptive use. The first one is the Blaney-Kreidel equation. Now it states that monthly consumptive use is given by this equation, where Cu is the monthly consumptive use, K, that is the crop factor determined by experiments for each crop under the environmental conditions of the area. T is the mean monthly temperature in degree Celsius or centigrade. P is the monthly percent of annual daylight hours that occur during the period. So this is the Blaney-Kreidel equation. Cu, that is the monthly consumptive use, that is equal to K into P divided by 40 into 1.8 T, that is the mean monthly temperature, plus 32. Now let we consider this P by 40 is equal to F. This factor, let we take it as equal to F. Then it can be written as that Cu is equal to K times F. It was found that K was too low for the short periods between irrigations. So the formula was modified as like this. Cu is equal to K summation of F. And also if K is variable, here we are assuming one value for K. If K is also variable, this formula can also be write down like this. Cu is equal to summation of K into F. Can be written in this form also. So where Cu is the seasonal consumptive use, that is consumptive use during the period of growth for a given crop in a given area. So using this equation, we can estimate the consumptive use or evapotranspiration for crops. Now in this equation, we have this K here. So this K, which is shown here, that it is the crop factor determined by experiments for each crop under the environmental conditions of that area. or there is a table available, monthly crop coefficient factor K, this is small k, for use in Blaney-Kreidel equation. So you can see here that we have rice, so value of k is 1.1 and a range of k that is 0.85 to 1.3. Similarly, we have wheat, 0.65 value of k, the range is 0.5 to 0.75 and so on. So you can see that for different crops the k values and ranges are given. So if we solve a problem and k value is not given, we can use this table to take the average value and use it in the equation to estimate the consumptive use. Similarly, in this equation here, this P is the monthly percent of annual daylight hours that occur during the period. So how to get its value? Again, we have this table available, monthly daytime sunshine percentage hours. This is P. That can be taken the value here for any location. This is, for example, for the north. It can be for the south also. So you can see here that 5 degree north, 10 degree clear. This is latitude in degrees here. So this shows the location of that area in the northern hemisphere. So for this location, for all the months, you can see from January to December here. So this is how the P value, monthly daytime sunshine percentage hours. So we can pick the value from here that we put in the Blaney-Kreidel equation to estimate the consumptive use for the crops. Let us solve a problem on this. We have this problem 2.9 from the book by Gerg. Wheat is to be grown at a certain place. The useful climatological conditions of which are tabulated below in the table. Determine the evapotranspiration, that is consumptive use, and the consumptive irrigation requirement of wheat crop. Also determine the field irrigation requirement if the water application efficiency, that is 80%. Make use of Blaney-Kreidel equation. So now in this equation, this table is given. We have wheat that is to be grown at a certain place. So now the months are given. We have November, December, January, February. Monthly temperature in degrees Celsius or centigrade averaged over the last 5 years for these months are given. For month of November, 18 degree centigrade, then 15 and so on for the other months. Similarly, the P value is given here for this question. If we do not have these P value given to us, then we can use this table for any location. Clear, for example, 10 degree north, then for the different months we can pick the value of P from this table. But here in this question the P values are given. So monthly percentage of daytime hour of the year computed from sunshine tables, which I already show you. And we have the useful rainfall in centimeter that is averaged over the last 5 years. For these months, the useful rainfall, that is the effective rainfall, so that is also given. Now first we have to calculate the evapotranspiration or consumptive use. So we already know that according to the Blaney-Kreidel equation, if we apply this equation here, so Cu, that is the consumptive use or evapotranspiration, that is equal to K, small k, into summation of F. And this F, that is given by P by 40 into 1.8 T plus 32. So what we can do is that now for the 4 months here, November, December, January and February, we have to calculate this F. P is given and T is given. We have this is the temperature and this is the P. So we can calculate So we have November, December, January and February that we can write down here. November, December, January, and we have February. Now we can calculate this F for these months. So now what we can do is that for November, this T is 18. So T is equal to 18 for November. That is degree C. And what is P here? 7.20. So P is equal to 7.20. So now you put in the above equation here and then we calculate the F value. So the F comes out to be 11.592. This is 11.592. Now next for December, we have the temperature is 15 and we have the P value as 7.15. So if you put in the above equation, this comes out to be 10.546. So this is equal to 10.546. Similarly, we go for temperature 13.5 and then P 7.30. So this is 10.275. And finally, we have the temperature is 14.5 and the P value 7.1. So F comes out to be 10.313. Now what we have to do in this equation, that consumptive use is equal to K into summation of F. So it means that we have to calculate summation of F. You just add these values. So summation of F, that will be equal to just sum of all these values. So this is equal to 42.726. Now in this equation that we have that consumptive use Cu or evapotranspiration, this is equal to this small k into summation of F. So if K is not given in the question, you see that we have wheat. So we go back and you can see here that for wheat, this is now wheat from this table. This is wheat, and we can consider the value of K is 0.65. So you can see that from table, three eight for wheat, this small k, that is equal to 0.65. So we just take this value here, 0.65. Now we can put the values here and we can calculate Cu, the consumptive use or evapotranspiration. That will be equal to 0.65 into 42.726. So this will be equal to 27.77 centimeter. Cu is in centimeter. 27.77 centimeter. Clear? So this is how we calculate the consumptive use. Clear? Now after this, what it is required, we need to calculate the consumptive irrigation requirement. So consumptive irrigation requirement, that is CIR, that is actually equal to Cu, the consumptive use, minus the effective rainfall. Minus the effective rainfall. So for this we need to calculate the effective rainfall for the 4 months. So in here we can calculate the effective rainfall. Just we need to add up all these values. 8.38 centimeter. 8.38 centimeter. Just we add up all these values. So we have consumptive use that we just calculated, 27.77 centimeter, and we have this effective rainfall that we just add 8.38 centimeter. 8.38 centimeter. So from here CIR, consumptive irrigation requirement, so that is equal to 19.39 centimeter. This is for the wheat crop. Also determine the field irrigation requirement. So the field irrigation requirement, that we just defined, that this is equal to net irrigation requirement divided by eta A, where eta A is the water application efficiency, that is given 80%. Now we have calculated consumptive irrigation requirement, but here we need to put the net irrigation requirement. What we can do is that we can consider this NIR, net irrigation requirement, is equal to consumptive irrigation requirement. And why we can consider this? Since no water is used for deep percolation. Since no water is used for deep percolation. So now what we can do here is that we take it as 19.39 and we have the water application efficiency as 80%, so 0.80. So we have this field irrigation requirement (24.24 centimeter). So the field irrigation requirement, that is 24.24 centimeter. The second method, we have Hargreaves class A pane evaporation. In this method, evapotranspiration, that is consumptive use, is related to pane evaporation by a constant K. Now this is capital K. In the previous equation we use small k, this is now capital K. So ET, evapotranspiration or consumptive use, that will be equal to K times EP, where ET is the evapotranspiration or Cu is the consumptive use, EP is the pane evaporation, and K is the consumptive use coefficient. So this is exactly similar to, if you remember, you studied in hydrology to estimate the evaporation from a water body. So there you use Kp, the pane coefficient. Clear? So this is the same concept here. Consumptive use coefficient is different for different crops and is different for the same crop at different places. It also varies with the crop growth and is different at different crop stages for the same crop. So in the absence of local figures for specific crops, the data given in table 313, here this is table 313, we have for different crops percent of the crop growing season from 0 to 100%. This is the percent of the crop growing season, 0 to 100% for different types of crops. We can assume or take the value of K from this table if it is not calculated for the local conditions. So the data given in table 3.13 recommended by Hargreaves can be used, and in this table actually the crops, they have been divided into these 8 groups. So we have group A, B, C, D, E, F, G, and the 8th group that contains paddy or rice. So in group A we have potato, cotton, maize, beans, etc. In the group B we have tomato, olive, plums. In group C we have onions, grapes, melons, carrots. Group D we have wheat, barley, etc. Group E we have pastures, other orchard crops, etc. These are the different crops. Group F we have oranges, fruits. Group G contains sugar cane, alfalfa, and the 8th group, that is rice. So different crops are divided into different groups. These are total 8 groups. And then for these 8 groups, that is, you can see here group A, group B, group C, group D, group E, F, G, and we have rice. So for different percent of the growing season, from 0 to 100%, these K values that can be taken from here in estimating the consumptive use or evapotranspiration. Class A pane evaporation measurement. This EP, it can be experimentally determined by directly measuring the quantity of water evaporated from the standard class A pane. So the standard class A pane, this pane is 1.2 meter in diameter, 25 centimeter deep, and bottom is raised 15 centimeter above the ground surface. So you can see here that the standard class A pane, you might have studied in hydrology also. This is a pane 1.2 meter in diameter, and it is 25 centimeter deep, and the bottom that is raised 15 centimeter above the ground in order to avoid any effect of the conduction of the ground on this pane. The depth of water is to be kept in a fixed range such that the water surface is at least 5 centimeter and never more than 7.5 centimeter below the top of the pane. You can see here 50 to 75 millimeter from the rim, from the top. So the water evaporates, and then the depth of water that is calculated. So this is how we can estimate the EP. This is another picture. You can see that sometimes we place the anemometer here to measure the wind speed also. The pane evaporation EP can also be determined by using the Christensen formula. So this is a formula with the help of which we can also calculate the pane evaporation. So this formula is EP is equal to 0.49 R into these coefficients CT, CW, CH, CS, and CE. So in this equation, this EP is the pane evaporation, R is the extraterrestrial radiation in the same units as EP in centimeter or millimeter, CT is the coefficient of temperature that can be calculated using this equation if we know the mean temperature, CW, that is the coefficient of wind velocity. It can be calculated from this equation, this coefficient, where W is the mean wind velocity at 0.5 meter above the ground in kilometer per day. CH, that is the coefficient of relative humidity, can be calculated from this equation, where H is the mean percentage relative humidity at noon or average relative humidity for 11 and 18 hours. CS, So that is the coefficient of percent of possible sunshine can be calculated from this equation, where S is the mean sunshine percentage and CE, that is the coefficient of elevation. So where E is the elevation in 100 meters, we can estimate this coefficient for any area if we know its elevation. So this is the Christensen formula, which can also be used to determine the pen evaporation. The third method that is important, that is known as the Penman equation. So Penman developed a theoretical formula based on principles of both energy budget and mass transfer approaches to compute potential evapotranspiration in the following form. Potential evapotranspiration that we defined earlier. So this Penman equation you might have studied in hydrology also when you study the chapter of evaporation. So there we have different methods in order to estimate the evaporation from a water body. So Penman developed this theoretical formula based on the principles of both energy budget method, where we consider the energy budget of the water body to calculate the evaporation, and the mass transfer approaches. Clear? So he combined these two techniques to compute potential evapotranspiration in this form. This is the Penman equation. In this equation, ET, evapotranspiration, that is equal to A into H plus alpha into E sub A divided by A plus alpha. So ET, that is the evapotranspiration in millimeter per day. We have this alpha, this is the psychrometric constant, its value is known to us, 0.49 millimeter mercury per degree centigrade or Celsius. A in this equation, this is the slope of the curve between the saturated vapor pressure and temperature at mean air temperature. EA, that is the drying power of air, which includes wind velocity and saturation deficit. Saturation deficit, that is the difference between the saturation vapor pressure and actual vapor pressure, and is given by this equation. EA is equal to 0.002187 into 160 plus U2 into ES minus EA. So 0.002187. This U2, this is actually the mean wind speed in kilometer per day measured 2 meters above the ground. This ES and EA, these are the saturation vapor pressure at mean air temperature, and EA is the actual vapor pressure in the air in millimeter of mercury, and is equal to ES multiplied by relative humidity. So if we know the relative humidity, RH, that is the relative humidity, so we can multiply with saturation vapor pressure to calculate the actual vapor pressure. And in this equation we have H. So this H is the daily net radiation in millimeter of water given by this equation. H can be calculated using this equation, where RA is the mean monthly extraterrestrial radiation in millimeter of water per day. This phi here, This shows the latitude of the place where ET, evapotranspiration, is being computed. R, small r, you can see here this small r. So this is the reflection coefficient of the surface. So these guideline values are given: 0.15 to 0.25 for close crops. For barren land, it is 0.5 to 0.45, and for water surface, it is 0.05. Similarly, in this equation, this small n here, you can see this small n here, and also it is here. So this is the actual duration of bright sunshine, which is a function of latitude of the place and is observed data at that place. If we do not have the values for this small n, alternatively it can be taken equal to p. Earlier that the table was available for p, so we can take this n as equal to p. Capital N, that is the maximum possible hours of bright sunshine available at different locations. And in this equation we have this sigma. So this is the Stephen Boltzmann constant. Its value is 2.01 into 10 power minus 9 millimeter per day. And TA, that is the mean air temperature. Now the wind speed that we have to include here, you see at 2 meter U2, wind speed in kilometer per day measured 2 meter above the ground. So if the wind speed is measured at any other height, can be reduced to 2 meter height by the relationship. This is the formula available. So this is the wind speed at any height z. It can be reduced to u2, the wind speed at 2 meter above the ground here. So these are the different parameters in the Penman equation. These are the tables available from where we can pick the values. This is the table for saturation vapor pressure. This is table 310, and these tables are taken from the book Irrigation and Water Power Engineering by Pumia. So you can see here that in this table we have this temperature. So for the given temperature, we can read the saturation vapor pressure and the slope of plot between 1 and 2. Means the slope of the plot between the temperature and between the saturation vapor pressure. So this is actually this A here. You see in the equation we have this A, slope of the curve between saturation vapor pressure and temperature. So from this table, this is actually A in the Penman equation. Similarly, we have this table 311, mean monthly solar radiation RA, that we can take for the months. It's from January to December, and we have the northern hemisphere, we have the southern hemisphere for different locations. Clear, for the given months we can read the value of RA. So this is the mean monthly solar radiation incident on Earth outer space, that is the extraterrestrial radiation in millimeter of evaporable water per day. Similarly, we have another table, table 3.12. We have maximum possible hours of bright sunshine in hours. This is the capital N. So we have the north latitude in degrees. This we can use because Pakistan is in the northern hemisphere. We can have this table for the south latitude in degrees. So we have this latitude in degrees and we have these months. So from this table we can pick maximum possible hours of bright sunshine in hours. And this is P, the small n that is given in the formula here, the actual duration of bright sunshine, which is a function of the latitude of any area. Alternatively, if it is not given, alternatively it can be taken as equal to P. So in this here table 3.9, this can be taken as equal to small n. So we have the latitude and we have for the months for the any specific location on the surface of Earth. We can pick the value of small n from here. Now let us try to solve a problem how we apply the Penman's formula and use these different tables to calculate the consumptive use. So this is example 3.19 from the Pumia book. Calculate the consumptive use or evapotranspiration of rice for the month of January by using the Penman's formula for the following data available at the field. So latitude of the place is 20 degree north, northern hemisphere. We have mean monthly temperature that is 15 degrees centigrade or Celsius, relative humidity in January for that place that is 50%, elevation of the area that is 250 meter, and wind velocity at 2 meter height that is measured as 25 kilometer per day. So now we already know that we have to use the Penman equation. So that is equal to ET, the evapotranspiration, and this is given as A into H. We have to now calculate the values for these different parameters, plus we have alpha into EA divided by A plus alpha. So now we have to use this equation, but as we discussed in the previous slides, now we have to calculate the values for these different parameters. So let us go and proceed step by step for this solution. So we are given the temperature. So for the mean temperature, that is 15 degree centigrade or Celsius, we go to table 310. So you can see here, first we go to this table 310, and now we are given the temperature 15 degree centigrade. This is temperature in centigrade. We have this 15 degrees centigrade that is given in the question. So we can read the value of saturation vapor pressure ES from here, 12.79. This is the value for ES, saturation vapor pressure, 12.79 millimeter of mercury, and also the value for this A. slope between the temperature and the saturation vapor pressure. So the value for A, that is also given from here, 0.80. So these two values we can pick, clear, for the given temperature of 15 degree centigrade. So from table, .10 for the temperature of 15 degree C, we read the values, that is the saturation vapor pressure ES, that is equal to 12.79 millimeter of mercury and we also read the value for the slope, so that is A is equal to 0.80, clear, 0.80. So this value of A, this is actually used in this formula here, A, in the numerator and in the denominator. Now next we have from table from table 311, what we can pick the value. So you see that the latitude is given as 20 degree N and we have the month is January. So we go to table 311. You can see this is table 311. Now we have the month of January. This is the month of January and we have location of that area is 20 degree. This is given in the question, 20 degree and month of January, so this is 10.8. This value we pick. This is RA, mean monthly solar radiation, clear, in millimeter of evaporable water per day, 10.8. So this value we pick from the table, that is RA, this is equal to 10.8 millimeter of water per day. This is for the latitude of 20 degree and in the month of January. Next we have from table 3.9. So we have from table .9. So in table 3.9, what we have, this is table 3.9 and we can estimate the value of the small n, that is taken as equal to P. So we have the latitude, so the latitude that is equal to, how much is the latitude here, 20 degree N. So this is the north, and we have this 20-degree here. And for the month of January, this is the value of small n, 7.74. So we have this small n that is taken as equal to P. So this is equal to 7.74 hours. This is for January, and latitude of place 20-degree N. Now we have this table 3.12 also. We have from table 3.12. From there, what we can read, again we have table 3.12 here. So we can read the value of the capital N, which is the maximum possible hours of bright sunshine. So in this table for latitude 20-degree, we have this latitude 20-degree, north latitude in degrees, and we have month of January. So this is the month of January here. This is now the value that we will pick. This is 11.1. This is capital N. So we have this capital N that is equal to 11.1 hours. So now we have taken these values from the different tables. Now what we can do is we can calculate this n, small n divided by capital N, because if I go back and see the formulas, you see that I need to calculate this small n by capital N, small n by capital N. So we can calculate these ratios. So this will be equal to 7.74 divided by 11.1. So this will be equal to 0.697, 0.697. Next we can calculate this EA, the actual vapor pressure. The saturation vapor pressure we have already calculated from this table 310. We have taken its value 12.79. So the actual vapor pressure, this will be equal to saturation vapor pressure multiplied by the relative humidity, RH. Now in the question it is given relative humidity in January, that is 50%. So we can put its value here, ES, that is 12.79. Into 0.5. So the actual vapor pressure, this is 6.395 millimeter of mercury. Hg, hydrogarium. Next we have to calculate this Ea. So Ea is here in this equation here, Ea, and Ea is given by this equation here. So Ea, that is equal to 0.002187 into 160 plus U2 into ES minus EA. This is the equation. So if you put the values, just plug in the values for all the parameters, and this will be equal to 2.59 millimeter per day. Next we have rice. This is given in the question. This crop is rice. We have to estimate the value of the small r. Clear? This small r here. So this small r here, this is the reflection coefficient of the surface. So because rice, you can see here for closed crops, it can be between 0.15 to 0.25. So we can assume the value from that range. For rice, we have this as a closed crop. So we can assume the value of small r is equal to 0.20. Next we have the alpha. So alpha, we already know that the value of alpha psychrometric constant, that is 0.49 millimeter of mercury Hg per degree C. These are constant. Clear? In the equation we already discussed them here. This alpha psychrometric constant 0.49, and we have the sigma here, Stephen Boltzmann's constant. This value is already known to us. So we have this sigma that is equal to 2.01 into 10 power minus 9 millimeter per day. So now we can estimate the value of H, the capital H here, that is given by this equation here, this equation. H we can estimate now in here. So this H value comes out to be 2.14 millimeter of water per day. Now in the equation, that is ET evapotranspiration, so this is equal to A into H. We have calculated all the values, plus alpha into EA divided by A plus alpha. So in this formula we can put the values. So this is 0.8 into H, that is 2.14, plus we have alpha, that is 0.49, into EA 2.59, divided by A, that is 0.8, plus alpha, that is 0.49. So from here we can calculate this ET evapotranspiration. This comes out to be 2.31 millimeter per day. Now in the question it is asked that you compute the consumptive use for rice for the month of January. So for January, we have this ET that is equal to 2.31 millimeter per day, and we have 31 days in the month of January. So this day cancel out, and we have this ET that is equal to 71.64 millimeter of water for January. So this is how we apply the Perman equation to estimate the evapotranspiration.